So in this video, I want to put emphasis in MO diagrams, molecular orbital diagrams, and how do we draw them, what do they mean? All right. So I put this picture here not to show anything else, but to just remind you guys that remember we said that, okay, well, we have some sort of spontaneity when our delta G is negative. So this vertical line here shows our delta G. So we have some sort of spontaneity when our delta G is negative, which means that a reaction will most likely occur. When the delta G is positive, however, above zero, it's non-spontaneous, right? So we got to put energy into that system in order for that to occur. These occur on their own, right? So just keep that in mind. Now, let's look at a simple molecular orbital diagram for, ethylene. Now, you look at simple molecular orbital diagram for ethylene. Now, ethylene looks something like this. All right, it's this molecule here. Now, the thing with MO diagrams is that we have to have sp2 hybridized atoms, right? In order for us to draw, show some sort of bonding, which has to do with pi electrons, these atoms have to be sp2 hybridized. So just keep that in mind. And we can see that these atoms, all these atoms here are actually sp2 hybridized, right? So let's look at the molecular orbital diagram. And what does it mean? Well, on the vertical line, we have a change in delta G, right? So this is our change in energy. Let me replace it with energy. And we say, okay, well, this could be a zero mark, which means that anything above, below here is negative, which means that, and we're talking about delta G, which means that a reaction is spontaneous. So we want to show bonded electrons below, right? Because our delta G is negative, there's spontaneity. Above, we have delta G is positive. Well, okay, well, if it's positive, the electron density is not there, right? Because the reaction is non-spontaneous. So the way we draw molecular orbital diagrams is that, okay, well, we count on how many pi electrons do we have. Well, in this molecule here, you can see that we have 2 pi electrons, right? Remember we said that every single bond is a sigma bond. Every sigma bond is a single bond, right? And then we said a double bond consists of one single bond, one sigma bond, and one pi bond. So we have 2 pi electrons here. So remember we talked about the off-ball principle. And we say in the lowest molecular orbital, we have to fulfill our lowest molecular orbital before, before we head to higher energy levels. So the way I'm going to do this is I'm going to draw my line. Right. Okay. Well, let's see. We have 2 pi electrons. So I'm going to put my 2 pi electrons. Remember, they have to be anti-spin like this, which represent these two pi electrons here. Right. So I have my lowest. So because we're showing maximum bonding in this orbital, this is what you'll commonly see referred to as HOMO. And this stands for highest occupied molecular orbital. I'm just going to shorten that. All right. Now, this is this is a negative delta G, which means that we want to show electrons here. Maximum bonding occurs here. Now, the number of lines that I put on the bottom, depending on how many pi electrons I have, should be equal to the number of, lines I put on the top. So if I have one line here, which I have no more pi electrons, I'm going to have one line above my delta G0, right? And this is where, well, if we're run out of electrons to give, there's no electrons here. And so this is usually, you'll see this commonly referred to as pi star or, LUMO. And this is a lowest molecular, lowest unoccupied molecular orbital. All right, which means that we're showing no bonds in here, right? So this is our lowest unoccupied molecular orbital. All right, so there's no electron. All the electron density is down where we have maximum bonding. Now, I want to talk a little bit of thing about nodes, right? So we represent p orbitals as usually some sort of node that looks like some sort of a pi electrons that looks like this. All right. So depending on how many pi electrons you have, that should be indicative of how many of these kind of S's you see. All right. So because I have 2 pi electrons here, I'm gonna have 1. I'm gonna have 2. Now, if I had 4, it would have 1, 2, 3, 4. So because I only have 2 pi electrons here, I'm gonna show that there's 2 p or two kind of these these S's right here, if you want to so call. They're not S's, but that's how I tend to look at it. Now, the way we show this is because this is our highest occupied molecular orbital, which means that there's bonding, and maybe I should emphasize this, or HOMO, right? Or when our delta G is negative, this is our bonding orbital. So this is showing bonding, this is our bonding orbital. We're showing bonding occurring here. Now, in the LUMO, there's anti-bonding. So these are the anti-bonding. Because there's no bonds here. We have maximum bonding here. There's no bonds here. So this is our bonding orbital. This is our anti-bonding orbital. Now, the way we show bonds with these is that we draw in a shade. And the shade has to match. The shade has to match. So if I want to show that there's some sort of bonding occurring here, then this shade has to match this shade. Right? They can't be opposite. So this is how we show that there's actually bonding here. Now, because we draw 2 kind of S's for a bonding orbital, we have to show the same for an anti-bonding orbital. So kind of right here, but let me squeeze it in. So I have 1, 2. Even though there's no electrons here, we're going based on our bonding orbital. So now we have 2 S's. Well, how do we? There's no bonding here, so how do we show that? Well, the higher you increase in energy, your nodes increases. So a node is usually typically represented as this dash here. Now, we got to show that these electrons are anti-bonding. We got to show that these electrons are anti-bonding. So how do we show that these electrons are anti-bonding? Well, we got to shade this in, right? Now we have a node here showing that there's some sort of, we're going up in energy, so our nodes increases. So we have 1 here. Now, because there's no bonds here, the next one has to go down here. I have to shade this one down here. And look, these do not match. We have a node and these do not match. So this is our anti-bonding orbital. We're showing that there's no bonds here. Down here, a HOMO, we're showing that there's bonds here, which means that we have our stuff matching together. So this is how we do MO for regular for regular sp2 hybridized systems. Now let's look at a more complicated one, and let's kind of bring the concept home here. So that is just a simple one. So let's bring the concept home here. So again, we're talking about delta G here. So we have our change in energy on vertical axis going up, and let's assume that this is 0. So let's see. Let's draw the molecular orbital diagram for this molecule here. This is actually called butadiene. Now, before I even go further, I got to make sure I have sp2 hybridized carbons. My system, well, not carbons, but atoms. My system has to be conjugated, and it has to be sp2 for the atoms. So you can see that here we have an sp2 hybridized carbon in this sense. We have sp2 here, sp2 here, sp2 here. So this system is all conjugated sp2 atoms. So we're good. So the first thing you want to do is count how many pi electrons we have. Well, we have 2 and we have 2, right? We have 2 pi electrons. Remember we said that each double bond is consist of a single bond and 2 pi electrons, right? So we have 2 pi electrons here. We have 2 pi electrons here. 2 pi electrons, 2 pi electrons, which means that in total we have 4 pi electrons. So how do we represent this? Well, because we have 4 pi electrons, well, going below where delta G is negative, this is where we want to show bonding, right? This is our bonding molecular orbital. We want to show maximum bonding here. So I'm going to draw a line, right? And I got to fulfill this line first. Well, since I have 4 pi electrons, well, I have 1, 2. Now this is max right here. I can't go anymore. I can't put, 3 or 4. That doesn't work. So once this lowest energy orbital is fulfilled, now the off-ball principle says I could go up to the next one. Now we have 4 pi electrons in total. So we have 2 here. So we got to go 1, 2. And this satisfies our 4 pi electrons for butadiene. Now, do we have any more pi electrons? No. So therefore, we have to skip over into our, if we have no more pi electrons, we have to skip over. We have to skip over into our anti-bonding orbital. Again, all our pi electrons are used. So remember we said that these lines, how many lines you have here should be proportional to how many lines you have in your anti-bonding orbital. So hence the reason why we had 1 line here. Well, we have to have 1 in our anti-bonding orbital. Same thing here. We have 2 lines here. So we have to have 2 lines in our anti-bonding orbital. So we have 1. Notice our delta G now becomes positive, which means that there's not, the reaction is non-spontaneous, right? So these will not cause our reaction to occur. So we have 1 and then we have 2. Now we are out of electrons to show. There's no more electrons. There's no more pi electrons. So again, this is our bonding orbital. Or no, I'm gonna hold off on that. And this is our anti-bonding. Right, so this is our anti-bonding. Now, here's where the concept of node comes in. This is where the concept of node comes in. So remember we talked about showing maximum bonding here and then showing non-bonding electrons here. Well, how many total pi electrons we had here? We had a total pi electrons of 2 pi electrons. So therefore, hence the reason why we had 2 s's. So 1, 2, right? Here we have 4 pi electrons. So we got to show, and you take your best guess, we got to show 1, 2, 3, 4 s's. All right. Now, remember, the lowest unoccupied orbit, the lowest bonding energy, or the lowest, usually one at the bottom, we got to show maximum bonding occurring there, right? Or we got to show maximum bonding occurring here. So if you want to show maximum bonding occurring here, well, this has to be shaded. This has to be shaded. This has to be shaded. And this has to be shaded. Right. So all 4 of these have to be shaded because what we're showing there is that there is maximum bonding occurring in this orbital. All right. So we're going to go a step further. So we got to draw 4 for this one also. Now remember, we said that the higher in energy we go, we get less bonding. So therefore, and this is something I should mention, these are very symmetrical. So we got to show symmetry here. So we have 4. Now, the higher we go, there's less bonding, which means that, okay, well, let's see. I'm going to have this bonding. I'm going to show that there's a bond between this. But remember, we said that the higher we go, we increase, we start increasing nodes. So how do we split these? Where do we split these 4 kind of S's in order to show that there's symmetry? Well, I have to split it here, right? So we're going to show that there's a node here. Now, these are bonded. Remember, we said that higher you go, we're getting into the anti-bonding electron configuration. So therefore, if these are up and we're showing that there's some sort of bond between these two, well, these have to be down to show that there's bond between these two, but between these four here, there's a node that splits it. And all this is showing is that we're going up. So we have to increase what we call a node or line. Now, let me specify this completely. A lot of people talk about HOMO and LUMO. And we say, okay, well, the HOMO, we usually specify it as the highest molecular orbital, the bonding orbital. Well, in fact, this is not our HOMO. This is actually our HOMO, right? Highest HOMO, yeah, that's not HUMO. So the highest occupied molecular orbital. Well, what does that mean? Well, this is lower than this, right? Because as we were increasing our delta G, right? So this is higher than this. So this is our highest occupied molecular orbital, not this one. So if we want to specify, this is our highest occupied HOMO. So the one that is closer to zero, that is negative, is actually your HOMO. So not this. So this is our HOMO. Now we're increasing delta G again. Now we're in the anti-bonding electron space. So therefore we still have 1, 2, 3, 4. Now how are we going to show anti-bonding and symmetry? Well, because I have one line here, as I increase, I'm going to have 2. Now, where would I split these two? Where would I put my lines to show that these are symmetrical? Where would I split my line to show that these are symmetrical? Well, I could put a line here. And I could put a line, let's see, I could put a line here. So notice that as I'm increasing, initially we started from 0 lines, then we go to 1, then we go to 2, and this is the pattern. All right, so you could use this pattern and apply it to any MO diagram you want of your choice. So now we got to show that there is there's not any bonding. This is the anti-bonding electron space. So how do we show that these are anti-bonding? Well, we could show that there's a shade there, but because these are anti-bonding, we have to show this one, the shade at the bottom. All right, we have to show that the shade is at the bottom. Now, what about these two? Well, I'm just gonna choose, but let's say I want to shade this in. If I shade this top in here, then this has to be shaded in the bottom. All right, this has to be shaded in the bottom. And look, we're not saying that these two are bonding, but it's just drawn in such a fashion that you look at them separately. You look at them as two different pieces. So we look at them as two different pieces. So just like this one, we look at it as two different pieces. So we say, okay, well, these two are bonding, these two are bonding. It's just we have a node here to show that we're going up in energy level. Now again, we look at them as two different pieces. So we show that these two are anti-bonding, these two are anti-bonding. Now, going to the last one, we still have 1s, 2s. Oh man, this is kind of messed up there. 3s, and let's see, 4s. Hope you guys can bear with me for that. All right. Now, again, notice that we had 2 nodes here. Well, take your best guess. We going from 1, 2, so we have to have 3 here. So how do we split this in order for it to be symmetrical? Well, we could do 1 here, we could do 2 here, and we could do 3 here. So notice that these are, I'm sorry guys, these are kind of spaced out in such fashion, it's kind of weird. So you know what, I'm gonna do it over here. So kind of ignore this one here. So we have 1, 2, 3, 4. For the last one, well, if we had 2 nodes here, this is 1, 2, 3. So 3, notice that 3 nodes actually splits it completely. And we're under anti-bonding electrons. So therefore we have, this is kind of, this has our shade. Well, if these are anti-bonding, this has to be down here, right? If these are anti-bonded, this has to be up here, and this has to be down here. So notice at any given time, we're showing that there's no bonding occurring, right? So totally ignore this. This is being replaced with this. All right. So, and let me emphasize this. Now this is our LUMO. So this is our LUMO, lowest unoccupied molecular orbital.